Uber now uses deep learning to predict arrival times, MuZero is used to compress YouTube videos, and NeRF scales to entire city blocks. Amazing. Welcome to ML News. Hey ho there, this video is sponsored by Weights and Biases. Today I want to tell you about a new feature in Weights and Biases, which is their integration with the OpenAI API. If you didn't know, OpenAI has the ability that you can provide your data and they fine-tune a GPT-3 model for you. Now this is pretty cool in itself because you get your own little custom endpoint that you can call, has been trained on your data, but now you can sync those training runs to your Weights and Biases account. All you need to do for this to happen is to simply call the sync command on the command line, and all your training runs will be synced to Weights and Biases. They have a little demo collab where they demonstrate that you can actually use the artifacts and tables features from Weights and Biases. Essentially anything that you know, you can construct your data sets, you can have them as artifacts, you can look at them in the tables, then you can ship them to OpenAI to do a fine-tuning run, and then you can analyze that fine-tuning run and the outputs of it again in Weights and Biases. They even have a little demo report where they do something like this. They upload a Wikipedia dataset, they analyze it first using tables, then they analyze the loss from the fine-tuning results. They do a little bit of a hyperparameter search, and you can analyze those in these nice parallel coordinate plots fully interactively. And in the end, they use this custom fine-tuned model in order to make predictions, and again, they analyze predictions using tables. So if you want to get started with big text models and especially using APIs such as OpenAI, it has never been easier than now. Check out Weights and Biases. They have all kinds of tools for machine learning researchers, practitioners, educators, students, and much more. Individual use is free forever, and they have great team plans, and they even do on-prem hosting for enterprise. With that being said, thanks again to Weights and Biases for sponsoring this video. Please check them out, and let's get into it. The Uber engineering blog has a new post up about how Uber switched from XGBoost to deep learning to predict arrival times. Uber itself is a massive business. It's not only ride-sharing, it's packages, it's food, and all of these things have in common that at some point there needs to be made a prediction of how long something is going to take until it arrives. Either the food, the people, the packages, you name it. So they used to have this big XGBoost model that predicted when stuff would arrive. And in the blog post, they detail that that just didn't scale anymore. They had more and more data they needed to incorporate. They wanted to get more accuracy, more diverse business cases, more locations. So they switched to deep learning. Now, what's pretty interesting right here is that the goal isn't necessarily to predict the arrival time. However, they have a traffic routing system already, which is essentially something like Google Maps. You type in where you want to go and where you are, and the routing system analyzes the individual pieces, maybe a little bit of traffic on them, and then predicts for each of the individual pieces how long it's going to take. You add all of that up, you get some sort of an estimate. Now, the problem is real life is more complicated than you can just estimate from a map and a bit of traffic data. So what the machine learning model does is it takes a whole bunch of features, discrete features, continuous features, which interestingly, they quantize first before feeding them to the model. They feed that into a transformer model, and from that, they predict a residual. So whatever they need to correct from the routing output. So they don't predict directly how long something's going to take. They simply predict how much it's going to deviate from the routing system's predictions. The system itself seems fairly involved. They don't just shove all the features into the beginning. They also have some features that come in later into the system. But I think the general principle of taking something like a base heuristic, like the routing system, and then simply predicting the residual might be a more general thing that I don't see used often enough. Now, maybe I just don't know and it's used all over, but I do think that we could layer our approaches much more than we are doing right now, because whenever people switch from something classic to something deep learning, they try to just sort of do all end to end. And maybe the approach of doing more of like a hierarchical prediction where every layer just predicts the residual from the last layer might actually be better. The blog post goes into detail how careful you have to be with respect to some of the features. For example, location is a very special feature, obviously, if you do routing, because you can't just encode the coordinates because the model needs to somehow know something about the 2D structure. So there's a location hashing algorithm where you can trade off accuracy versus storage. There are also various considerations with respect to the loss, where they use the asymmetric Huber loss, arguing, for example, that being 1 minute too late is much worse than being 1 minute too early. So this lets the engineers tune the system in concordance with business decisions. They also describe how they train this thing and then finally deploy it. What's impressive is that the predictions come back in the order of milliseconds, which is pretty cool. Yeah, it seems like a big jump in performance for the Uber estimated arrival times. If you want to learn more, please check out the blog post and the Uber engineering blog. DeepMind has released a blog post called MuZero's First Step from Research into the Real World. Now, MuZero is an iteration on the AlphaZero algorithm. The difference being AlphaZero still required an internal simulator. Therefore, it only worked for systems where such a simulator was available. For example, games like chess and Go. In these games, you can do a step and you know exactly how the board's gonna look like. And you can reverse the step again. You say, oh no, I actually don't want to do that. I want to do something else. You can use that for planning into the future. You can start multiple times, explore different paths, and so on. There are, however, environments where this is not possible. For example, pretty much anywhere else in life. MuZero overcomes this by building a latent model in which it can plan forward. So there's no explicit simulator required. So MuZero is more general than AlphaZero and has matched or surpassed AlphaZero in many domains. Yet it still sort of lacked a real-world application, because even for MuZero you need giant amounts of data to train this thing on. Now it does make sense that video compression is a really good application for something like MuZero. So what you do in video compression is you look at a video frame by frame and you try to transmit that sequence of frames over the network. Therefore, it should be as small as possible, yet still retain a lot of its quality. In order to do that, usually codecs are used, not codecs with an X, codecs with CS at the end. This is a piece of software that describes how to take video frames or sequences of video frames and represent them as a compressed data stream. Now, this is not a static function. In fact, how much a series of frames is compressed is controlled by this thing called the quantization parameter. The idea is if you have a slow scene, very static, like a green background or just a face talking, you can compress large parts of the images and you can compress them for a long time because they'll just be the same a minute from now. So you can crank up that quantization parameter without losing too much quality. However, if a scene is fast moving, if there's lots of stuff happening on screen, you cannot compress the image as much because over time things change and therefore there's more information on the screen. Even though you might think this is not useful information, it is image information, and therefore you cannot compress the image as much. Now, current codecs use heuristics, engineered heuristics, to determine when I can crank up or down that quantization parameter. And that is kind of an ideal setting for something like MuZero. You feed it a bunch of videos, you say, here's a target quality that I want to reach, and you let MuZero decide on the quantization parameter essentially for each frame. This is a sequential decision-making process. You need a bit of outlook into the future to see what's happening later, how much can I compress now, what should I do? So it's very much in the framework of these reinforcement learning problems. Now, I have looked at these videos, and so this is kind of the original video, okay? And cool. All right, now let's look at the MuZero compressed video. Like I cannot see a difference. So the bit rate saving is the idea that I can't see. Ah, I get it. Okay, maybe it's the idea that I can't see a difference. And they tell me that MuZero uses 4.7% less bits to encode that video sequence. 4.7% might not seem like a lot, but given that apparently most internet traffic nowadays is video streaming, this is a giant saving. Now, I still don't exactly know how much overhead there is running MuZero at inference time to do the compression. But fair to say that savings like this make a real difference on our already overloaded internet infrastructure. If you want to learn more, check out the DeepMind blog post. There's also a paper going along with that called MuZero with Self-Competition for Rate Control in VP9 Video Compression that goes more into the details of how they trained the system. It uses a concept called self-competition, which is kind of akin to self-play, and it's a lot more technical than the blog post. The Google AI blog has a new entry called Guiding Frozen Language Models with Learned Soft Prompts. Also here, there's a paper going along with that called The Power of Scale for Parameter-Efficient Prompt Tuning. This prompt tuning is an interesting concept of a novel way. In NLP in recent years, we've had two basic modus operandi, whatever. The first one was kind of like the BERT mode, where you take a pre-trained model like BERT and you fine-tune the model on your data, meaning you provided input-output pairs and you fine-tuned either the whole model, adapter layers, or just the head or something like this. And then on the very other end of the spectrum is something like GPT-3 that is pre-trained and will just remain fixed for the duration of its lifetime. And what you can do is you can prompt it, which means that you have to come up with clever things that you can put in front of your question to make GPT-3 output the correct thing, which is usually called in-context learning. This paper, they're not the first ones doing it as far as I'm aware, but it is an interesting concept and it's taken a bit to the next level here, is that why are we coming up ourselves with that stuff to input? Can't we teach a model to automatically come up with that stuff? So if we have a data set, that might actually work. So what they do is they make the prompt input of the model into tunable parameters. So this is trained on data, so you need to have data in order to train this, but you'll keep the model completely frozen and you'll only tune what they call the soft prompt. So you don't necessarily determine the tokens to input into the language model, but you do tune the input vectors, so the embeddings of the tokens if this were the prompt. Now this obviously gets a bit less interpretable and so on, but it is a cool concept, and I do believe that it is a very parameter efficient way to steer these large language models. So in this particular paper, the specific task they tackle is sort of a multi-task training regime where for each task they tune one of these prompts, but I believe this can go further. These prompts are, you can see right here, it's 20,000 parameters for a prompt. Then that can steer a model of 11 billion. That is a factor of, I don't like 6 zeros or something like this. And I think that's really cool because it gives us a handle on these big models, and I'm excited to see what we can do if we push this to the limits. Block-NeRF is a new paper coming out of UC Berkeley, Waymo, and Google Research, and it pushes NeRF to the next level. What it does is it essentially takes an entire city block with Waymo cars going around, photographing stuff, and then it constructs many different individual NeRFs. A NeRF is a neural radiance field. I have made a video somewhere about that if you're interested. Essentially, it is a 3D representation that you can render from any angle, and it will faithfully represent things like, you know, when stuff looks different if you view it from here or from here. It's not perfect, but is really, really good. And the point is, no one needs to sit down and make the 3D models. You simply provided a bunch of pictures and it figures out itself how the stuff looks in 3D. Now, this used to work in a limited setting with like one object in the middle or one scene, but this paper right here takes an entire city block and figures out how to combine different NeRFs, like different scenes, together and stitch them together. They have a website that goes along with this with various videos where they showcase the power of this. So notice they're not even limited to the path that the cars originally drove on. They can just render from completely new points of view. This is really cool, and the scale of this is unprecedented. If you want to check this out, visit their websites. They have many videos available, and yeah, give it a try. And another post from the Google AI blog called Unlocking the Full Potential of Data Center ML Accelerators with Platform-Aware Neural Architecture Search. That is quite a long title, but what it describes is a paper that's called Searching for Fast Model Families on Data Center Accelerators that extends neural architecture search to also consider the underlying hardware. Usually neural architecture search is where I have some sort of an engine, like an evolutionary algorithm or something like this, slapped together a bunch of modules and parameterize them, and then I care which of them gives me the best end accuracy or something like this. In this particular case right here, they also worry about which models perform best on the underlying hardware. So you might know that things like TPUs and GPUs, they're good at some things and bad at other things. And their general layout of how they do computation, how they do memory access is very specialized to certain things. If you can make use of those things, if you can design models that inherently do very, very optimized memory access and so on, you can potentially speed up models by a lot while not sacrificing performance. All you do is you build a model that is better able to utilize the underlying hardware. So the final result of this paper is a model family called EfficientNet-X. EfficientNet-X largely matches EfficientNet, which is sort of a classic computer vision model. It largely matches that in terms of accuracy, yet it is much faster because it uses the underlying hardware a lot better. What the paper also does is it decouples the measure of flops, floating point operations, from actual performance. So people used to estimate how intensive, let's say, a model is by counting the number of flops that a forward pass would utilize. If a forward pass would utilize more flops, then the common assumption was, well, that sort of uses more compute and probably it will take longer. But EfficientNet-X requires double the amount of flops than EfficientNet does, and therefore people would say that it should take longer. However, it is 2 times faster on the appropriate hardware for which it was designed. This is an error rate of 400% if you actually consider flops as a measure of performance, which is crazy. So I think if anything, this paper shows that we need to rethink how we think about performance, and that maybe just flops is not necessarily a good measure of how we estimate model compute utilization. This is a blog post from the Flower team. Flower means, I need to look this up, Flowing Epigenetic Robots and Systems. This is a research group that investigates things like cellular automata, artificial life, self-organizing systems, self-maintenance, and much more. This is a very lengthy blog post that goes into detail in some of these areas, into a system called Lenia, and into various connections with neuroscience, with self-organizing systems, with biology, and so on. They even have some interactive demos, so as you can see right here, there are these life forms. Now you can spawn more of these life forms, and to be said, these life forms, they are not somehow controlled top-down. They're self-organizing, self-perpetuating, even avoiding obstacles they do themselves. Now, I can, in fact, draw a bit more of an obstacle right here. You can see the evasion still works. It's pretty interesting to see what happens if you just put multiple of them. They do have collisions with each other. You can generate attractors to which they are going to be try to reach it. Come here. So if you feel tired of supervised learning, of having centralized parameters, of having a single model that does things and has overview and has top-down control, and if you feel like you want something different, something more emerging, then give this blog post a read. As I said, it's a long blog post. It goes into detail into various systems, starting from very simple systems and then going up into various experiments, various research papers on the topic. As I said, it explains the system called Lenia and much more. So yeah, can only recommend if you want something out of the box. There's this tool called Know Your Data by the Tensorflow Datasets team, and it is a very, very good TensorFlow dataset analyzer. For example, here the pre-configured query is, please give me images in the ImageNet dataset that have in their metadata a latitude above 72.09. Now, as you can see, a lot of pictures are, in fact, from sort of let's say, colder regions of the Earth. Now, it's not always going to be right, but this is a very valuable tool if you want to debug your datasets. It integrates with a lot of stuff. I already mentioned metadata, but it also integrates, for example, with cloud vision. So it will give you statistics of what cloud vision detects in these various images. You can also use that as filter. For example, now I would only like to get pictures that have a probability of containing a face above a certain amount, while also being very high in their latitude. Now, apparently there exist no such pictures. So let me clear one of the filters, and as you can see, there are some pictures where there might be faces. Now, ImageNet obviously doesn't have many faces as such. You can see this picture that does contain faces contains them from some sort of a print article. This tool can be used for many different things. You can analyze stats, you can analyze relations between things, you can inspect the data, and especially if you have your own data sets, this can help you discover problems with the data, discover biases, systematic distortions, and so on. There's a bit of an explanation page to go with it. You can see you can filter, group, and much more. However, your datasets do have to be supported by the TensorFlow Datasets API. All right, some helpful things for this week. Just helpful things, not even libraries, just things. I guess the last one was already a helpful thing. Casual GAN Papers on Twitter says, OpenAI stealth released model weights for the largest clip models. So apparently their repo now says they've released the largest clip model weights. If you're into clip, go get them. On neural differential equations is on arXiv, but it's not just a paper, it's an entire PhD thesis by Patrick Kidger, and it serves as a little bit of a textbook on neural differential equations. So if you're into that, check it out. PGMax is a library that implements general factor graphs for discrete probabilistic graphical models. Graphical models have been a little bit forgotten, at least in the mainstream deep learning world in recent years, but they were really cool before AlexNet promise. So this library, among other things, implements differentiable loopy belief propagation in JAX. So if you do work with probabilistic models on graphs, give this library a try. Diambra is a arena for AIs. It is multiple things at the same time. So first and foremost, it is a library, essentially reinforcement learning environments, mainly for two-player fighting games right now. So they say they feature a collection of high-quality environments for reinforcement learning research and experimentation. It's compliant with the OpenAI GYM standard, and it includes classic fighter games such as Dead or Alive, Street Fighter, Tekken, and so on. They do have a YouTube channel where they show some baseline implementations of reinforcement learning agents, and they do also host tournaments in these games. It's kind of like a Kaggle competition, I guess, except your agent is paired up against another agent, and then they play Tekken. If you're interested, check out Diambra. Python FHEZ is a privacy-preserving, fully homomorphic encryption and deep learning library. This library supports a lot of primitives in the areas of doing deep learning on data that you might or shouldn't have access to, that is private, that is secure in some form or another. And homomorphic encryption allows you to run certain calculations in an encrypted fashion or transmit information in an encrypted way, such that either one or the other party doesn't necessarily get to know all the contents of the data. So this being combined with deep learning is pretty cool, and this library enables that. Torch Metrics is a project by the PyTorch Lightning devs, and it implements metrics for PyTorch, especially for distributed and scaled up PyTorch. Computing metrics is often a hassle because you need to accumulate over batches or over different machines and so on. This library reduces that boilerplate and lets you just track and export your metrics in a very easy way. Here is a simple example that tracks the accuracy over a bunch of batches, I guess a batch of batches, if you will. So it does compute the accuracy on each batch, but it also keeps track of all of them. And then at the end, you can get your accuracy over all of the data. Now, if you've ever done this, you know that last batch is always trouble. If it's not exactly full, your metrics will not be perfectly accurate. And yeah, it seems like everyone on the world is just implementing the same thing. So good that there exist libraries. Yingtao Tian tweets that their work on modern evolution strategies for creativity has been accepted, and they've provided 2 new collabs that you can try out. So this work is very special. It's evolutionary strategies that try to make these collages of things. It uses clip and abstract shapes to achieve some visual goals, and it looks pretty sweet, I have to say. So now there's 2 collabs where you can try it out. Related to that, EvoJax's hardware-accelerated neuroevolution. In fact, if you have paid attention, the collabs from right before are in the EvoJax repository. So this is a JAX library that enables neuroevolution, evolutionary search, anything like this. And it enables a lot of cool stuff that is kind of outside the box for classical deep learning. On the right is one of these collages that I've just mentioned, and on the left is a little game where the agents have to collect food but avoid poison, and all of this is trained using evolutionary strategies. There's a paper to go along with the EvoJax environment if you're interested more. And lastly, Reddit user JKTerry1 writes that 5 months after taking over maintenance, I'm happy to announce that Jim now has a proper documentation website for the first time in its life. If you don't know, Jim is a project started by OpenAI and then abandoned by OpenAI and has been taken up by an open source developer who was kind enough to continue this project. And now under gymlibrary.ml, you can find proper documentation for the Gym library. Now, given how prevalent Gym still is, this is pretty cool. It's clean and simple, and if you do work with Gym and maybe you want to learn something new about the things that you've been using all along, check out this website. All right, this was it for ML News this week. I hope you had fun, and I'll see you next time. Bye-bye.